First of all, Bruce, thank you very much for the honor and for this opportunity. And I really mean that I am your disciple, and I'm a reader of stuff written by Bruce Supernaut. Bruce is our friend. He is a coach. He's a mentor. Sometimes he's a tormentor, challenging us to be better. And I think he's also been a very powerful grounding rod in the industry to help keep us real and keep at least 1 foot stuck in the real concrete. Of course, for many of us over a long time, Bruce has been a very successful member of a powerful team. Some people talk about Bruce and Ward, and then there's another group of people who talk about Ward and Bruce. And while we're looking at an image of Ward, how many of us in the room consider ourselves one way or another to be a consultant? All right, excellent. You need to know Ward's mantra for consultants. If you can't be part of the solution, there is money to be made in prolonging the problem. All right. I found this online. For many years, Supernaut was a fixture at the World of Concrete, often appearing as the master of ceremonies for the mega demos in jeans, work boots, and a tuxedo shirt, jacket, and bow tie. And he usually didn't go with the classy wedding type short jacket. He usually went with tails. And I searched and searched and searched to get a photograph of that, and I was disappointed that I could not. So Bruce was doing black tie and blue jeans before it became a thing. You can go to events which are listed as black tie and blue jeans. So Bruce, you are definitely a fashion trendsetter, without doubt. He is a man of many moods, and you saw some of these pictures here, and another picture that both Colin and I managed to find online is this one. And I was trying to figure out exactly what Bruce was doing there, and then I realized, okay, this must have been after one of his trips to New Zealand, and he was trying to be. Sometimes before a pour starts, Bruce will actually get out there and do a haka, which is kind of scary. Okay. Now, Bruce's wardrobe goes way beyond black tie and jeans, and as you saw a preview, one of the T-shirts in his collection, it's not cement, it's concrete. The other one he wears frequently is Concrete Whisperer. I like the smooth is my middle name, and the I am a concrete finisher. I don't stop when I'm tired. I stop when I'm done. And that is an absolute statement of Bruce as well. A great T-shirt that he has is my people skills are just fine. It's my tolerance to idiots that needs work. And the thing that's so ironic about that is Bruce wrote the book on tolerance. So he can wear that shirt. Another one of his shirts that he wears, sometimes to ACI meetings and sometimes to church, is I didn't mean to push all your buttons. I was just looking for mute. But the one that needs to give all of us pause is don't piss off old people. The older we get, the less life in prison is a deterrent. All right, so my topic is overdesign, and it's absolutely complementary with the wonderful and detailed things that Eamon just taught us. And I think his news you can use per minute ratio is going to be higher than mine. So if we're talking about overdesign, you will hear this throughout the industry. And one of the things I haven't heard from the field is somebody complaining, this concrete is too thick. This pavement is too wide. There's too much rebar. There's just too much concrete on this job. Somebody must have overdesigned. No, you guys love it. The more concrete, the more steel we can put out there, the more money you can make and lose. So not too many complain about that aspect of overdesign. You don't care if the if the engineer doubled the thickness of the slab, bring it on, okay? So I think most of the time when people are talking about overdesign, they are talking about the topic that Eamon so thoroughly covered. The focus on the so-called overdesign surrounding the 28-day concrete cylinder compressive strength, the so-called F'(C) or specified strength. That technically is a specified 28-day strength of lab cure compressive strength. But then, exactly as we just heard, to get a number from the laboratory that is worthy, that is qualified to be used to assess the quality of the concrete, it's got to be cast per C31, initially stored on the site for up to 48 hours without moisture loss, 60 to 80 degree air temperature, and that is limited to 68, 78 if you're looking at 6,000 psi or more. And in fact, it says shielded from direct sunlight, which is in fact a direct copy of the Roman Empire's imperial concrete specification written by Marcus Vitruvius in his book, which is entitled On the Nature of All Things. And he says aggregates for concrete need to be shielded from sunlight and from moonlight. And ASTM decided, well, we got to do that. In fact, there was always this thought that people who were exposed to too much moonlight would go crazy, and that's the source of our word lunatic. And I've also heard that only lunatics would wait 28 days or one full lunar cycle to test their concrete. Anyway, it's over that time period without moisture loss at a temperature range. And then tested in a moist condition. If that cylinder looks dry and dusty and light gray, it shouldn't be tested. It needs to be tested moist and loaded at 35 plus or minus 7 psi per second after the first 50% of the load. If it's a late Friday afternoon and the boss at the testing company says, I'll tell you what, as soon as you finish up all those cylinders, head home for the weekend. Man, it's going to be load, bang, and that's good news for the contractor. A late Friday afternoon cylinder break, those numbers are going to go up. Monday morning, the boss says, okay, I need these cylinders broken today, and when you're done, you can clean out the moist room. The test guy's going to say, I got to figure out a way to make this last all day long, and we very slowly load, and the strength is going to go down, okay? And they have to be loaded until the test operator is, quote, certain that ultimate capacity has been attained. Now, the problem with testing all the way to ultimate capacity is you got a lot of fragments and parts and pieces and dust that you have to sweep up. So if you just load them until they start saying, ouch, ouch, stop the machine right there, you'll get a low break, but the cleanup is a lot easier. So exactly as the prophets foretold, the testing has got to be good. Now, when we're talking about this overdesign that people like to swear about, let's just take an example. Let's say you got a specified compressive strength, 5,000 psi, but then some clown comes along and says, well, the truth is it said 5,000, but we really meant 5,470. And that brings out all kinds of responses. That 470 psi is usually referred to in the field as that blank overdesign, and you can fill in that blank with whatever expletive you would like to have, colorful or off-colorful. Okay, so what are some of the misinterpretations? That this costs money, consumes resources, carbon footprint. Yes, it can. Anytime we put more cementitious material in, we're going to cost money and consume resources and carbon footprint. But even worse is the misinterpretation that this is arbitrary, it's conservative, it's some sort of building code imposition. It's a convoluted way to get higher strength than specified. It's going in the back door. This is the specifications, bait and switch. They told us 5,000 in writing, but now they're telling us 5,470. And it might cause people to say, why in the world didn't they just specify 5,470 instead of the 5,000 that they wrote in the specs in the first place? All right, those are interesting issues. Now, some constructive interpretations would be that this increases the safety and reliability of concrete structures for all users, all passersby, all future owners. It helps to define the tolerance for the acceptability of our strength test, and it can reduce the time and cost spent dealing with and arguing with low breaks. And these were also on Eamon's list. Now, where does that F prime C come from? Many of you know this exactly. Part of the F prime C comes from the engineer's calculations based on the mathematics and the mechanics of what compressive strength do we need to assume in this structure to be able to provide the necessary resistance to load. But there's another side of that coin. There's another independent source of what F prime C we're going to need, and that's going to be based on providing adequate resistance to the environmental exposure. And going all the way back to the 2008 edition of the 318 code, that's when the environmental exposure system was introduced to try and quantify the environmental resistance that we need. So that was born as a result of NRMCA's P2P initiative. The F0, it's not exposed to freezing and thawing, up to the F3, which may only be with us a few more years. That's exposed to freezing and thawing. It's wet, and we got de-icing salt on it. The C0, there's no real corrosion risk. The C1, it's kind of moderate. The C2 is now we've got some real chlorides in place. And there's others for sulfates and moisture and that sort of thing. All right, so the design engineer is required to clarify what is the intended exposure classification, and then you work through the fine print and some charts and tables, and you end up then associating minimum specifiable compressive strengths that are connected to various exposure categories. So for a bit of an example that I want to run today here, let's say that this structure is going to be exposed to salt. It's going to be exposed to freezing temperatures while it's wet, and we are concerned about corrosion of reinforcing steel. So that would bring us to an F3 that says 5,000 psi is the minimum specifiable value, and the C2 tells us the same thing. If we have an intense corrosion environment, we're going to need 5,000 psi. Now, interestingly, where do these numbers come from? If we were to take the ACI 211 default values for the relationships between water-cement ratio and compressive strength, the solid line there is non-air and train concrete. The dash is air and train. So we see as the water-cement ratio goes down, that strength is going to go up. And then if we would also take a look at, say, for example, some old Bureau of Reclamation information about how water-cement ratio influences the permeability of the concrete, we would say that if we want a more durable concrete with a lower permeability and other related transport properties, and we want a high strength, then that's going to throw us down to this region of the curve, and kind of this association here where if it's going to be moist and freezing, without the de-icing salt, we want to be right around in here at a water-cement ratio of 0.45 or less. That would intersect the 211.1 data at about 4,500. So a number like 4,500 becomes a minimum specifiable for a freeze-thaw environment. If we then say, well, I need even lower permeability, let me go down here to around a 0.4 to come down on this permeability curve. Yeah, that's going to help keep the water and the salt and the oxygen and the CO2 and the pets and the small children from being sucked into the concrete. And then we run that up, and that's going to intersect the air and train curve at about 5,000. All right, so there's some justification for these numbers. However, one of the things that is real is that permeability or transport property relationship is absolutely unique to every set of materials, every different type of cement, every different type of SCM, whether we're talking about a type 1, a type 2, a type 3, a 1L or a 1LMNOPQRST, whatever the version happens to be. And in fact, sometimes late at night, the police ask you to give you those letters in reverse order. Now, since those relationships are mix specific, I think there is no question about it that that wide range of other modifications on the mix gives us some room. We need to do some work there, and I know Colin and Doug Hooten and a number of people have been working on that. All right, so anyway, that's where that comes from. So let's take a quick example here. We got C2 corrosion, we got F3 freeze thaw, and let's say the structural engineer designed it for 4,500. When the design calculations were done, 4,500 was picked. If we take a look at our C2 and our F3, that says 5,000. So what was supposed to happen here, and you say, all right, I've got a strength and mechanical properties requirement, I've got a durability requirement, the highest requirement is going to govern. So we got a minimum specifiable value of 5,000 psi for a structure that maybe looks something like that. And Bruno, these steps look even worse than when you were on campus. Okay. All right, so we got the 5,000 psi. Now, if the specified strength is 5,000, is it okay if the average strength is 5,000? Well, let's look at that. Here's the good news. If your average strength is 5,000 and your required strength is 5,000, then let there be dancing in the streets, because half your brakes are stronger than required. But unfortunately, there's not going to be peace in the valley, because half your brakes are weaker than required, and that gives you about a 50% chance of meeting the spec. So imagine in that pre-construction conference, you're talking to the structural engineer, and you say, we promise you, we're going to meet your strength requirement at least half the time. Okay, that ain't going to fly. All right? So if your average has to be higher than the specified, how much higher? And that's where we go into the mysterious land of the so-called overdesign. What would be the lowest average strength that you could have that would be consistent with meeting those requirements 99% of the time? Let's be bold. Let's go all the way to 99. And that's the question that we're posing here today. And what I want to share with you is that's not all that unusual of a question for all kinds of other applications. For example, a related overdesign problem. How much extra time do you allow to get to the airport? Because you got to pack your car, you got to get in the car, you got to back out of the driveway, you got to remember what you forgot, you got to pull back in, you got to go grab whatever that is, underwear, chapstick, your laptop, whatever it might be. Then you head down the road, and then you get to the airport, and then you look and look and look for a place to park. This is almost precisely what happened to me last Friday morning at Syracuse Airport, okay? And then you got to get to the check-in and get rid of your suitcase, and then you got to go through TSA, and then eventually you stand in the jetway as your plane is gone. All right. Now, this will be no surprise. Nerd that I am, I've been tracking this. My longest time to Syracuse Airport after 37 consecutive trips is 130 minutes, a little over 2 hours. My absolute shortest. And man, I was sitting down on it for that one. That was 62 minutes, but on average, it's 93 minutes. So if I would say, okay, I'm going to depart for the airport in 93 minutes before I have to be there, half the time I'm going to make it. That's really pretty good. Okay, so but also half the time I'm going to be saying goodbye to my my airplane. Now. So how much extra time do you allow to get to the airport? And you've all got an answer to that question, okay? And I'll tell you, last Friday morning, I wish I had put an extra 15 minutes on that baby, okay? Now, is that extra time that you are allowing to increase your chances of not being left at the gate and then being told that the next plane to San Francisco is sometime in August? Is that extra allowance that you provide an overdesign? Okay, there's a thought. Now, here's some good news for you. A very good friend of mine from New Zealand, Andrew Dallas, past president, New Zealand Concrete Association, once told me, Ken, he says, Kane, if you never missed a plane, you are getting to the airport too early. Okay, so, you know, how close to the edge do you want to live? Okay, now let's do an entirely different analogy. Let's look at a target. And let's first of all talk about the difference between accuracy and precision. Accuracy would be represented by how far the center of your shot pattern is from the center of the target that you are shooting at, okay? And precision is how tight your shot pattern is. And I'm looking at Larry here, and if we're not careful, he will pull out his pistol right now and shoot out this screen. And Larry, I'll bet you put about 6 right in the center there. Okay, so precision. All right. They confiscated that at the airport, right? Okay. And you tried to tell him this is a visual aid for Kent's talk. Okay, all right. All right, now, the common measure of precision is that we take a look at how far from the center of the shot pattern would you have to go to draw a circle so that you would cover 68%, let's call that 2/3, of all the shots. So if we said we had a 5-inch radius from the center of the shot pattern, what that would mean is 2/3 of all of our shots are within 5 inches. Okay. Now, let's translate this to another problem. The famous legend of William Tell, revolutionary soldier in Switzerland and Europe's greatest archer, and one day he offended the town magistrate, so the town magistrate punished him by saying, "You're such a famous archer. What we're going to do is tie your son to a tree, and then you've got to use this great crossbow of yours, and you've got to hit the apple that we're going to put on his head." All right? Now, let's ask Bill Tell to go out to the field, first of all, and shoot a whole quiver of arrows into that target. And then let's get a bunch of nerds and measure how far all those arrows came. And if we found out that 2/3 of all those arrows were within 5 inches of the center of that shot pattern, we could then call that a standard deviation, which is much better than a non-standard deviation, that is for sure. All right, so that would mean that about 1/3 of your shots are more than 5 inches high, low, or wide. Okay. Now let's go back to Bill and his son. All right. So we're shooting, and if he's got a 5-inch standard deviation, then this is bad news. Okay. That means there's 2/3 of those arrows are going to go within plus or minus 5 inches of the apple. That also means that from the apple down, there's a 50% chance that actually is going to kill his kid. That's not good. That's not good at all. All right. So what's the solution to that if the rules of the game would permit? Well, let's raise the stupid apple. But this is cool. How far we raise the apple is going to depend on the skill of the archer. Now, let's say Bill's having a bad day. We would have to raise it way up to there. But what if the child's mother shows up and she is really good? We can lower that apple back down. Why? Because she is a better and more precise archer. Okay. Now, what if we get men in tights to shoot? We better put that apple 5 or 6 feet above. All right, now that is what we are trying to do with Overdesign. We got a whole bunch of people who depend on the quality and the integrity of that concrete, and by how much are we going to raise that target to make sure that those people, and not just the owners, but the people who work and live and play in that structure, the people who happen to be walking by that structure or parking in it, how are we going to keep them safe enough? All right, so we're going to raise it up. And we're going to raise it up based on what is the standard deviation, but not a standard deviation that we'll find in a code, a standard deviation that is unique to a particular concrete producer, with the idea that the better, the tighter the precision of a given producer, the lower we can drop that target. That's why there isn't a fixed number for how much the overdesign is. The overdesign is a function of the skill and capability of that producer. Okay, but here is some breaking news which really messes up the game. That standard deviation which we're going to use there is not just a representation of the concrete producer. When the standard deviation gets high, the general interpretation is that the concrete producer is getting a little on the sloppy side. No, the standard deviation is based on data for concrete made by the producer, sampled and tested by the test lab. So if the test lab's a little sloppy, it's going to look like the concrete producer is a little sloppy. So that standard deviation, that really is a joint venture. Okay, all right. So the required overdesign depends on the individual producer's unique value of standard deviation. So we could take a look at some actual cylinder breaks there, and exactly as you just saw, what we're going to find normally is periodically there's going to be some breaks that are lower than F prime C, but we don't go to the wall and hit the panic button as you just understood, okay, or as you just heard, all right? So every now and then this is going to happen, okay? This is the every now and then you have a bad day. And then the question is, how bad does a day have to be to cause you to talk to your spouse about it when you get home that night? Or perhaps not talk to anybody when you get home that night. And the definition of a really bad day is when an individual strength drops more than 500 psi underneath. And that's the one that we're saying, if that happens one time in 100, all right, okay, that is just part of life as we heard. Okay, so we get the average, and we can figure out the arithmetic of the standard deviation, and we can say, yep, 2/3 of all of our cylinders are going to be in that band somewhere, and we can use that, and we can run with that ball, and we can calculate the standard deviation. So occasionally we all have suboptimal days, and that's just life. Okay, that's nothing to quit our jobs about. Now, another really cool thing that we can do is not only record the individual test results, but to record what's known as the running average of 3. The individual test results say, yes, every now and then you get a bad test for any number of possible reasons, from production to testing. The running average of 3 starts out by taking those first 3 tests and getting their average, and then you shift over one and you get the next average, and you shift over one and you shift over one. And what that does is filter out a whole lot of the noise in the system. And what it does is start to reveal to you systematically what is happening with the production and the testing. So when you plot the running average of 3, you end up with a tighter, you get the same average, but you end up with a tighter band. In fact, that standard deviation is only about 58% of the original standard deviation. So you use that. And what we're worried about here is systematically, when we're looking at test after test after test after test, we're looking at the overall program, that's where we don't want them to dip down underneath the specified value. But if that happens 1% of the time, that's okay too. Okay, so we get data from the producer. We got an average concrete strength of 5560. We got a standard deviation of 350. That's a coefficient variation of 6.3%, which ACI 214 would say this is excellent. This is excellent quality control. When we do the standard deviation for the 3-cylinder pairs, that's 202. Now, what's the lowest average strength that would signal 99% specification compliance? Okay, that's the question. Now, sadly, to answer that question, we have to go through the looking glass, and we're going to use some probability and statistics, and that probably is the signal to evacuate the room here immediately. Eamon was very gentle. He put some normal distribution curves up there. He didn't dwell on them because he knew that that would be like pulling the fire drill. All right, so we need to use probability and statistics, and why? Let's say we're using 4x8 cylinders, for example. Do you realize that out of an 11-yard truck, you could make 2,554 4x8 cylinders? That's possible. That would be what the cool people call the sample space. And we're going to use 2 of those to tell us about the concrete. And the volume of those 2 4x8 cylinders is 0.04% of the volume of the concrete in that 11-yard truck, okay? So there is a lot of concrete in that truck for which we have absolutely no data. And we just have a little bit of a clue. In Night Moves by Bob Seger, one of the great phrases was, working on mysteries without any clues. And we are almost there. We are working on mysteries with just a tiny bit of information. And statistics helps us fill in the blanks to estimate the strength of the vast majority of the concrete in the structure that was not tested. We got hard numbers from the lab. That tells us what was tested. The question is, what's the next break going to be? And what's the break in 3 trucks from now going to be? And that's where statistics comes into play. And we're going to use the same mathematical principles of risk, chance, and probability that keeps the lights on in Las Vegas. And we all know that Las Vegas is a series of monuments built by those who understand these principles for the sole purposes of taking advantage of those people who do not understand those principles. Now, let me give you an example. Let's say you're playing poker and you're sitting down at the table and you've just been dealt 5 cards. And you're sitting at that table and you're holding 5 cards in your hand and you're trying to size up what the situation is. Wouldn't it be amazing if you got dealt a royal flush? Oh man, bet the farm right now. Of course, that'd freak everybody else at the table. That's why that's not going to happen, because you only have a 0.00015% chance of being dealt a royal flush. So you're holding your 5 cards. Those are your test results. You know the value of those 5 cards. What you don't know is where the other 47 cards are. They might be 2s. They might be aces. So you got to make a bet based on having a little tiny bit of information to make expectations and estimates about a lot of stuff that you don't know. So we take that cylinder test data and we group it into a diagram like this, which is called a histogram, in which we take all those cylinder breaks and we bin them into different categories. Okay, so that's real. Those are the real numbers. But what we don't know is filling in the blanks. Where are all the others? So a standard technique is to take the histogram, to take those blue lines, which are real, and turn them into the orange bell-shaped curve, or the normal curve, which is called the normal curve because it is absolutely normal. It is what you typically would expect in this kind of evidence. And what's the beauty of making this bizarre statistical transformation? All of a sudden, now you have a basis to start talking about the numbers that you do not know yet. So we can make a better estimate of the much larger data set once we make that transformation. And Eamon showed you these curves. But he was smart enough to say, let's let Ken fight with these. Okay, all right. And I'm not smart enough to do a good job of it. Okay, so this is now what we are expecting from the concrete that is not tested. And all that statistics boils down to a couple simple equations. Our target strength is going to be specified strength plus this, 2.33S, and for our 5,000 PSI example, we got a bargain in the industry today. Tell you what, we're going to mark that strength down 500 PSI. Mark them down and move them out. So we're going to give you a free 500 PSI. And then we're going to say, I want a 1% risk of getting lower than that. Then we're going to take that running average of 3, because we're more worried about a systematic error than an everyday bad day. You know, pretty much the code says if you have a bad day 1 day a week, don't quit your job. If you have 3 bad days in a row, you might be thinking about a career change. And that's essentially what the code is saying here. So we run those particular numbers, and for the values that we're using in this example, 5,000 PSI was the specified value. 5470 would be the number that Las Vegas gives us. But the good news is that the average strength of that mixture the concrete producer demonstrated was 5560. So you've got an average strength that's higher than the required target strength. And as the cool people would say, you are good to go. And as was pointed out, if you can pull that standard deviation down, if you can pull the scatter down, if you can shoot a tighter shot pattern, then you can reduce that. And that is going to require a partnership not just between NRMCA and ASCC, but NRMCA and the testing organizations, because they are both contributing to that scatter. Collins' organization could deliver cylinder after cylinder after cylinder that's identical, but if the testing is all over the place, we're going to get an S, which is big. So if you can pull the standard deviation down, and there's physical limits as to how low that could be, then what can happen is you can pull down your required strength. And I think Eamon made that point much more clearly and a whole lot faster than I just did. Okay. All right, so some conclusions. So-called overdesign has a solid rational basis. The so-called overdesign is not arbitrarily conservative. It's conservative, but not arbitrarily so. Greater precision in concrete production and testing can reduce the target strength in the cementitious material. And my other conclusion, Bruce, it's an honor to help recognize your career influence on the built environment, your influence on our industry, and your influence on our institute. Thank you very much.